rather scrubbing over that I've only told you one quantum number here for the vibration. So why have we got a whole slew of lines in here? So that's the topic we're going to move on to now, because basically the take-home message is that all these spectra with molecules, the rotations change. So with the vibrational excitation, you change the rotations. With electronic excitation, which we'll do probably this afternoon or maybe tomorrow, you also change the rotational structure. Very strong rules for that, and they give. Someone was asking me about assigning spectra. How do you actually understand what the quantum numbers are? Well, actually, the rotational motion gives you clues, at least in simple spectra. You can read some of it from the rotational structure. So let's flick through this. So we have the selection rules that by the end of this course should be ingrained in your consciousness. Delta J is plus or minus 1 or 0. Okay, it was true of atoms. It was true of the rotational motion we did yesterday. It's true of vibrations, and we'll see it's true of electronic spectra. And J is a good quantum number if you don't have the hyperfine in there. So this is not a propensity, this is rigorous. And knowing, as you should have gathered by now, how resolution spectroscopy likes having funny terms for everything. It has names for these branches for the rotations, which are PQR. And actually, if you get changes, and we'll come to changes where delta J is 2 in quadrupole transitions, you keep on expanding the alphabet outwards. I have no idea why someone centered it on Q in the first place. So why delta J is 0 is a Q branch. And then when it goes down, you go P and lower down the alphabet. And when it goes up, you go ST, etc., up in the alphabet. But that's how it is, and that's what it means. So if you look at a diatomic spectrum or a linear molecule spectrum, a rather higher resolution than the ones we were just looking at. So for some strange reason, this is in frequency units, but it's only going from 8 to 9.2, so it's a relatively small region. And you can see here that you get a pronounced band structure. So there's a lot in this, actually. First thing to say is when you get these simple spectra, the line which actually just corresponds to vibrational frequency is not there. It's there by a gap. So we've already discussed you now have a J0 to J0 transition. This would be J0 to J0. It's not there. So you end up, you can see the band origin, as it's called. In these simple spectra, you can see it as a gap in the middle of the thing. So you start here and you count outwards. So this is, get this right way around, this is the P branch this way. So this is going 1 to 0. This one is going 0 to 1. 2 to 1, 3 to 2, 4 to 3, 5 to 4, 6 to 5, etc. So you just count out from the middle. Doesn't necessarily, well, if it's a diatomic, you can guess which vibrational mode there is because there's only one. If it's a polyatomic, it doesn't necessarily tell you which vibrational mode this is. But you can actually do the rotational assignment in a simple case just by looking like this. If you have a closed shell system, and someone asked me what open shell and closed shell is yesterday, it's simply whether you have unpaired electrons, we have angular momentum from the electrons. So a closed shell system, I said already yesterday that if you have, say, 2p6 or 1s squared, you get S equals L equals J equals 0 for the atom. That's a closed shell. So you get the same for a molecule. If there's no angular momentum, so no spin, no orbital angular momentum, you get something which has no affects the electronic structure on this. So for a closed shell diatomic, you never get a Q branch. So there's never delta J0, so you always get this gap in the middle. I think we've mentioned two diatomics and one polyatomic, which are not closed shell. Oxygen is not a closed shell molecule, it's actually a triplet ground state. NO is not closed shell, it's a doublet pi ground state. And I'm not going to go into the complications of the vibrational spectrum of a doublet pi ground state, but you can imagine you've got the pi is doubly degenerate, the 2 is doubly degenerate, so you get 4 lines instead of 1 for everything. And the other one is N02, which is even more complicated. So complicated that I haven't yet managed to do a decent calculation on N02, and we won't explore that. So the vast majority of molecules you get these spectra for are closed shell. So they have this, you don't have to worry about the electronic structure when you're doing this at all. It has no fingerprints in the spectrum. Right, we have each of these lines is doublets. There's a clue on the picture. What are we looking at here? In terms of why have we got 2 lines instead of 1? Isotopes, very good. And as I said, there's a clue on the picture because it's actually marked up for you. This is HCl, and as I said yesterday, chlorine has this slightly unusual property that 3/4 of it is chlorine 35 and 1/4 of it is chlorine 37. So you get 2 lines in each case. The separation of energies, if it's completely harmonic and rigid, it's going to be constant. But because it's not, it does change slightly, and we'll come back to that when we do electronic spectrum where it changes a lot. Okay. You can also get the thermal population. I talked about getting a thermal population out of a rotational spectrum. You can get out of a rotational spectrum. It's quite unusual to take the whole rotational spectrum in one scan. It's much more usual to take a vibrational spectrum like this out of one scan. So to be honest, you tend to use for thermometry these vibrational spectra more than the rotational spectrum, but it's the same rules. You get a rotational distribution here. The peak one is somewhere between, so what do we say this? This is the R branch. So this one is 0 to 1, 1 to 2, 2 to 3, 3 to 4. So it's somewhere between J equals 3 and J equals 4. In this case, it's quite cold. And you get the same distribution here. I've written it 2 ways. You can write it in terms of partition function. But if you want to do the little exercise I said to find the formula for the maximum, it's easier to do it in terms of the population of the ground state, because that doesn't vary with that you get a simpler formula to differentiate, and it gives you the same answer. The partition function depends on T, so you end up having to do a complicated differential. So you get, this will give you a temperature based on this rotational distribution of intensities. So, isotopes. Having shown you isotope spectrum with the chlorine 37 in it there. So the harmonic oscillator, I already gave you this formula in terms of what the energy is. H cross omega, which is the fundamental frequency. And then vibrational quanta, I've called them V there. I may have called them N elsewhere, but it's just the counting number going from 0 plus a half. Omega in the harmonic approximation is something called the force constant. So it's actually, these things obey Hooke's law, actually. Interesting comment on Hooke's law in the Publish Can Perish Well. He published it as an anagram. Do you know what an anagram is? It's where you mix up the letters. His was a particularly spectacularly boring anagram. He simply put all the letters in alphabetic order. So it had about 5 I's in it. And he left it like that for 10 years till he thought someone else was going to discover it. And then he revealed what his anagram is. And it was, my Latin is not very good, but it was as the force, so is the extension in Latin. It's only 11 letters you can do it in, so it was a very small anagram. So anyway, harmonic oscillator is just Hooke's law, which says that as you stretch something, the extension is proportional to the distance you stretch it. But in quantum mechanics, you don't. That's the force. You deal with the derivative, you deal with potentials, and that's what gives you the curve for the harmonic oscillator. And by Hooke's law, the strength of you get something called the force constant, which is conventionally called K. And the fundamental frequency is simply the square root of the force constant divided by the reduced mass, with some fiddling around in units to get them all in the same units, because they're not necessarily all in the same units when you start off with, but it's basically that is the relationship. So the important point here is that there are isotope shifts here, but they depend on the square root of the reduced mass. If you remember, for the rotations, they depended one upon the reduced mass. So they're bigger for the rotations than they are for the vibrations, but this, well, you can see it's still visible because this spectrum, which is not spectacularly high resolution, you can clearly see the twin peaks of the isotopes. And if this was DCL, it would be even bigger because the effect of putting deuterium instead of hydrogen is large. So I don't know how many times you've had this formula, but it should be ingrained in your head by now. Sorry, I've got the inverse of it, haven't I? Sorry, that should not be ingrained in your head. I've written it upside down. Thank you very much. Let's correct it in real time. So the reduced mass has units of mass. It is a mass. So that's mass times mass divided by mass. So you can quite clearly see that I've got it upside down there. There's another way of writing it. That's the same formula. You can manipulate that into that. So you've got pronounced isotope shifts that depend on the square root of the inverse of the reduced mass. So this is still a way of getting nice isotopes. So far I've shown you a spectrum which had P and R branches in. Q branches, sorry, I need to keep on forgetting to do this, and I was warned by Bobby that you needed to do that. Yep. Q branches are rather spectacular, because actually in the harmonic approximation, every single line lies on top of each other. Now you can see here, they're not quite on top of each other. If you look at that at low resolution, let's go and draw it, but I think I've got a picture later on. Let's just see. You just get a spike. And this is acetylene. So here, it has, as we already discussed before, the break has several vibrational modes which are infrared active. And I think the straight stretching ones like this don't have a Q branch, and I think the bending ones do have a Q branch. There are rules depending in what direction the dipole changes, and I'm not going to dwell on them. So, if anyone was paying attention yesterday, any ideas why the line intensities alternate? And I'll give you a clue. We've got identical atoms in this thing. So we've got two identical hydrogens, two identical carbons. Any suggestions why the line intensities alternate? You can see where the pronounced alternation is. It's 3 to 1 between even and odd lines. Any suggestions? Some looking faces. Sorry? No, it's all one molecule, so it's not to do with isotopes. This is all just HCCH. Any other thoughts? Well, to get the intensity, you have to make it being asymmetric. So that's the reason of getting a transition intensity at all in the first place. So the symmetric one doesn't have an intensity, the asymmetric one does. So you need that for the transition. It doesn't give you, there's something else giving the alternations. Yep. That's true, but it doesn't give the alternations. So yeah, the intensity is proportional to the square of the change in the dipole. It's not why. The alternation is actually to do with the population of the states. So we did this yesterday, but you're probably not associating what we did yesterday on this. So to be a bit more explicit, this molecule is 1 hydrogen, 12 carbon, 12 carbon. If it was, for instance, 1 hydrogen, 12 carbon, 13 carbon, 1 hydrogen, the spectrum would look a bit different, but there would be no line alternation here. And the reason is because of the Pauli principle. We talked about the ortho-para states in hydrogen. The two hydrogens here are identical. The two carbons are identical, but they're both, I haven't shown you this, but carbon 12 has 0 nuclear spin. It's a both. So interchanging the two carbons doesn't do anything. So it's all about interchanging the two hydrogens. So we worked all the way through this for hydrogen molecule. This is actually hydrogen molecule just with two carbons that don't do anything stuck in the middle. So I could work all the way through it again, but it would not change 1 iota from what we did yesterday. And you get ortho-para. So the big lines are the ortho lines, the small lines are the para lines. Anyone remember whether ortho was J even or J odd? If you remember, it came down. Actually, I will go through it a bit. It's just, it was phi electronic times phi vibrational times phi rotational times phi nuclear. Okay? And I said yesterday we could ignore those two. We could ignore the vibration electronic. Here we can't, because I've already said some of the motions are asymmetric. And asymmetric means you have another parity in there. Okay? I think this is a bending mode, which is a symmetric mode. So ortho and para if for an even vibrational state, the ortho states have J odd, so they're J1, 3, 5, etc. And the para states have J even. Actually, thinking about this, we have to be going to an odd vibrational state, otherwise there's no spectrum. So you have to go from, this is a bit more notation. 2 dashes means lower state. 1 dash means upper state. So the lower states are J odd for ortho, they're the strong ones. The upper states are J even. We're changing J by 1. So actually we're changing the symmetry of J. Because that means we have to go from an even vibrational state to an odd vibrational state. So this intensity alternation is caused by the ortho-para behavior, by the nuclear spin statistics. And as a consequence of the Pauli rule, Pauli principle. Okay. Anything else on this before I move on? Right. So obviously you've got the R branch here and the P branch here, and we've got the center here, so you can count out this one be 0 to 1, 1 to 2, etc., going up the thing, and then you've got the Q branch, which is all the delta J equals 0 on top of each other. And actually sorting out that Q branch, even if you go to very high resolution, can be quite difficult because they really do lie very close to each other. One solution to this is to cool your molecule down, because then you get less lines. Because as soon as you cool it down, then that population of the lines gets less So intensity alteration due to nuclear spin statistics. Right, this is astronomical spectrum, ISO with the Infrared Space Observatory, which flew, so data on here, it flew about 20 years ago. It was the first really successful infrared telescope for taking molecular spectra. And I just want to do a comparison between, so solid state objects, and I'm not talking about solid state objects in this course, but qualitatively the spectra are very different. I just want to emphasize that. So you can take spectra of dust and other solid state objects in space, and people do, but they're lumps. They don't have any detailed structure in them. And this is not a matter of resolution, that's just how they are. Whereas you can see here for CO, we've got a nice line spectra resolved. You can see the band center here, and you can start counting outwards. We can also see this is either a bit noisy or it's not in equilibrium, because you don't get a completely smooth behavior. I think it's actually just a bit noisy. The telescope hasn't recorded something that smooth, but you can see the general contours of the spectrum. And this is in wavelength units, so the gap between the lines are not quite constant because there's reciprocal energies. But probably on this scale you can't see too much difference between the gaps, but there are slight gaps. And this thing is a dense molecular cloud. It must be reasonably warm because you've got lots of CO lines there, going up to about, I don't know, J10, 12. So that's reasonably hot. Okay, so something for you to think about. I think this is CO again. Doesn't really matter. Can you assign the lines on this spectrum? Have a think about this, get a bit of paper out, see whether you can assign what the rotational lines on this spectrum are. What I want to know is which J has the maximum so we can get a temperature from it. So have a think about that one. We've got some ideas. Anyone want to see me with a line that they can assign? Someone to give me a line, or do I have to start pointing at people? Got a possible line you've assigned here? Sorry? yeah, J values, yeah.
Right-hand side is like negative.
Yeah, that's right. Very good spot. This wave number scale, the wave number scale is going backwards. So this is indeed the P branch. Yeah. Yeah. So this line here is sorry, it's doing this line here, and this is so the lowest line you can have is 0. So the upper state is 0, and the convention is you write upper lower. So it's J prime, J double prime. That's upper, lower. And you do that even if it's an absorption, even if it's going from lower to upper, you still write it upper lower. If you want to indicate which way it's going, you can put an arrow in there rather than a dash, but you always write it upper lower. So that's 0, 1. Anyone want to offer me what this one is? 1, 2. We're going to go up to the peak, so sorry, I'm not writing it very well. 1, 2. Next one. 1, 2, 3. Next one. I think this is the peak. 5, 6. Okay. So this means that J lower at the peak is 6. Okay. Any offers from someone else what this line is? Someone? 0, right? So that starts at 0. The lowest state is 0. First one is 1. Next one. 2, 1. Come on. Is the temperature the true temperature, the initial state for both of them? So it should be, I'm saying in both of them, it's roughly 6. Okay? The formula, which I was just hurriedly looking up again in my book while you did that, is that J equals KT upon 2B to the half minus a half, gives you the approximate temperature. So we've got J equals 6. So 6.5 equals KT upon 2B. I'm going to say B is 2 just for simplicity. This is, so we have T equals, well, so it's 2 times 1.93 to be honest, divided by 0.79. Have I missed anything out? Times 6.5. Divided by 6.5. No, times 6.5. Anyone got a calculator? Give me a value for that. So if you remember, sorry? No, that doesn't sound right. This must be bigger than that. 2 times 1.93 times 6.5 divided by 0.79. 16 is going to be about 30 or 40. I think Kelvin, something like that. 31, okay. To be honest, the way we've done it, it's probably not good to 2 figures. One figure number. To do it properly, you fit the whole spectrum, and then you get a more accurate temperature. But it tells you this thing's about 30 Kelvin, which is sort of warm interstellar medium temperature. So that you can analyze the spectrum this way. Now, if this thing is at 30 Kelvin and it's out in space, how do you observe it? Because it certainly isn't emitting. This line here, center of this line is maybe 2,500 degrees in excitation temperature, because it's the second radiation constant is 0.79, so one wave number is 0.79 Kelvin. Sorry, 1 Kelvin is 0.79 wave numbers, so you need a lot of temperature to get up there. So you're not emitting, so how do you observe it? It's not an easy answer to this question, because normally the answer is you don't. So actually, to observe an observe an absorption spectrum, you need a light source. In a lab, that's easy. You put your stuff in a tube and you fire a laser, or you fire something down the tube, and that's a standard way of doing spectroscopy. In space, you can't go the other side of your interstellar cloud and put a beam there, so you have to find a light source, and the light source you generally use is a star. So you have to find a star that's the other side of your cloud that you could observe against. And that's why most detections are not done in the infrared. They're done in the radio frequency, very long wavelength. So you can just look at the natural absorption and emission of light at very low temperatures. So the 10, 20 Kelvin, you can see the rotational structures like I showed yesterday, just naturally occurring. You don't need a light source behind them. But if you want to look at the infrared, you have to do it against starlight. And that's a problem. We had a bunch of molecules, methane, for example, not CO, because CO has a dipole, but methane, for example, has no rotational spectrum. So if you want to observe methane in the interstellar medium, you have to do it against a light source. And that makes it much harder to observe methane. How do you observe nitrogen? There's a question for you. Most common molecule in our atmosphere. Has it got a rotational spectrum? No. Has it got a vibrational spectrum? Anyone know where the electronic spectra are? Way up there. It's a really strong band system. The answer is, frankly, you don't. So actually, in virtually everywhere in space, we know there's oxygen there. We have no idea how much it is. It's basically like it's translucent in our light. In our atmosphere, the light just passes through it. That's true as well. If you're going to see nitrogen, say, in the interstellar medium, and I'm sure there is nitrogen in the interstellar medium, you need a really high energy light source behind it, and you need something in space capable of detecting that, because you wouldn't get it in the Earth's atmosphere. So you can't see everything. Spectroscopy is great. You can't see everything. Right.
So you don't see any isotope.
So 15N, 14N has an incredibly weak dipole. 15N, 14N plus has a small dipole, and that would be observed.
Still not.
That would be observable, but I'm not. The trouble is the ions don't tend to live; they're just reactive. That would be observable. But the dipole, due to the failure of the Morgan approximation, is very, very small. So quadrupole lines tend to coordinate better than that. I know quadrupole lines of CO2 have been observed on Mars, so I suspect you can see for one of the solar system planets, you may be able to see quadrupole lines of nitrogen. I'm not going to do. Right, so that's a rather crude version of the same thing, and what I wanted to emphasize here is that if you look at low resolution, the Q branch just looks like a big spike. And if you really don't have very much sensitivity, that may be all you see. It's a very strong feature that you can see at low resolution. When we do electronic spectra, you'll see there are things called band heads, which have the rather similar property for different reasons. And you look at that structure, I've got my wave number scale the right way around this way at the time. So you can instantly say that's PQR. And that's the bending mode of CO2. That's what we're all worrying about for global warming. Okay? And you can see that this is really saturated. Actually, the Earth's atmosphere, even these ones are all saturated. So I made vibrational spectra sound easy. Of course, you've got these pesky asymmetric tops, and then they're a mess. Because the rotational structure is all over the place. So this is an absorption spectrum due to water, obviously with a bit which is optically thick here, because you just got lines all over the place, and it's really difficult to assign it. So 30 years ago now, I think we assigned a spectrum of hot water in sunspots. And my collaborator, Nikolai Zobov, was rolling through doing the assignments by hand, doing, I think, about 800 lines a month. There were a lot of lines in this spectrum. He gave up when he assigned several thousand lines, which is only about 20% of the ones there. And I now have a student doing machine learning. He's just started last month. His PhD, the idea is to do machine learning of assignment of molecular spectra. And one of my aims is that we should be able to assign the other 80% of the lines without costing Nikolai Zobov 3 years of his life to go through hand by hand, calculating them, comparing them, etc. So for these things, it's not at all straightforward. And you can't look at them. There's no nice PQR branch. They're all spread all over the place. There are PQR lines in there, but they're all overlapping. You can get a general feature that this branch is to do this vibrational motion, but you can't look at it and say, oh, that's what it is. As is traditional, we have the special hydrogen section. So by now you know what the dipole moment of hydrogen is. 0. Very good. So we don't have a dipole here. So everything I've just said applies to dipole transitions, doesn't apply to hydrogen. But as I said before, there's a lot of hydrogen in the universe, no dipole allowed rotational vibrational transitions, but it has a quadrupole. So it undergoes very weak quadrupole transitions. If you think of it, because it's orthopara, and I said that the hydrogen yesterday, I said yesterday that the even para states and the odd J ortho states behave like they're two different molecules. That means if you're doing jumps, they have to be even, otherwise you'd be changing the molecule and the photon will not change. Well, photons can change nuclear spin, but it's incredibly weak. So basically photons don't change nuclear spin. So you go in steps of 2. So the quadrupole rules are that delta J changes by 0 or 2. And this is where I said you go further down the alphabet. So O beyond P one way and S beyond R the other way. So you get SQO transitions. And these are very weak, factor of 10 to the minus 8. However, they're quite easy to see in space. So this is the Orion molecular cloud. Very bright in the winter. The way my bathroom is configured at home, if I stand at the bathroom window and look out in December, I can see Orion with the famous belt and all the rest of it. It's a very well-known star-forming region. Lots of hydrogen, quite bright, glows. I had a collaboration with a Swiss astronomer doing observations of this molecular clouds in Orion, and we got observing time 2 years in a row. One was on Christmas Eve, and one was on New Year's Day. These are the 2 biggest holidays in the Western calendar. So they were not very kind to us, but that's the time of year you can see Orion best. And the interesting thing was we were actually looking at trails of H2 emissions, and they were 2 years apart, and these trails had moved. So we were able to actually get the velocity, and the velocity was huge because these things are very distant. Anyway, so this is just a snapshot. You can see that it's the vibrational band origin in hydrogen. I think there's 4,400 wave number, so it's quite high up. This is S branch, so it's plus rotational transitions on top. These are the Q branch. This is high enough resolution that you're separating Q1, Q2, and Q3. So I haven't told you this notation, so let's do that. Sorry, lots of notation in this topic. Yeah, that's right. So the notation is you always give the lower j, so j double prime. So if you have all right, because I'm doing quadrupoles here, we'll have s as well. So if you have s, j double prime, that means 3 to 1 means the upper state is 3, that's called j prime. J double prime, the lower state is 1. And the standard way is to give the branch P, Q, R, S, whatever, in brackets, and then the quantum number of the lower j state. And that is a general notation. So much so that it's programmed into my Excel spreadsheets when I want to convert this from branch notation to quantum numbers. I have little Excel programs that do it for me. So the Q branch, obviously J stays the same. So this is 1 to 1, 2 to 2, 3 to 3. We've got S0 there, so that's 0 to 2. We've got S1 there, that's 1 to 3, and S2. And then we've got vibrationally excited states here. So these, the ones without the vibrational labels and these are in emission, so they're given an arrow going downwards. This is a hot object that's glowing. It's basically creating heat because it's forming stars. So question for you. Why is this line much brighter than those two lines? And it's not temperature. So this one is odd J, that one's even J. What are we doing here? This is hydrogen. Any ideas? Sorry? So what's the question is, why are the lines, why is the S1 line much bigger than the S2 and the S0 line? I'm telling you, for free, it's not due to temperature. There's some other effect in here. It's causing this line to be much stronger. So I would guess 3 times stronger. So what we looked at, which causes the intensities to alternate between transitions. Yeah.
Maybe the population of hydrogen in that particular population of hydrogen.
So yeah, it's to do with the population of hydrogen, but it's something specific to do with the population of hydrogen.
That's why it is.
Yeah, so it's to do with the population levels of hydrogen, but they're so specific. Why should the odd level of hydrogen be much bigger than the even level of hydrogen? Just to encourage you all, you've got an exam on this on Friday. And you may have the advantage you can do it in pseudo-anonymity when you write on your bit of paper, but you're going to expect it to know questions like this for Friday. So why is this 3 to 1 here, or roughly 3 to 1? We already discussed this for settling before the break, which is also a similar observation. Sorry?
Odd J is ortho and even J is.
That's exactly right. So this is nuclear spin statistics. Sorry, my writing is terrible. Ortho to para is 3 to 1. And it's caused by the nuclear spin statistics in the system. Now, actually, in interstellar medium, where I've already said you get very few collisions, ortho and para may not be thermal. So you get a nuclear spin temperature on top of any other temperature. And nowadays people are doing chemistries, treating them as two different molecules and doing reactions with ortho hydrogen and para hydrogen separately, as if they're different species. And I don't know whether it's 3 to 1 or it looks actually slightly more than 3 to 1, but that's just my eye. But it's ortho para, as you say. That's right. So next question. Who was awake on Monday? What line's that? That's BR gamma, if you can't read it. Anyone remember what line that is? What species do you think it is? What's the commonest species in the universe? What? Sorry? No. Good try, but completely the wrong direction. What's the commonest? Bromine is not a common atom. What is the commonest atom in the universe? Hydrogen. Right. So this is hydrogen. You spent Monday, well, I wasn't here, well, I was spending Monday at Delhi Airport studying hydrogen. So this is a line in hydrogen. Which line is it? Yep. Bracket. Gamma. So anyone want to tell me what the quantum numbers for bracket gamma are? So gamma means a change by how many quanta in n? So alpha is 1, beta is 2, gamma is 3. And bracket, bracket is the one above Balmer. So Lyman alpha, Lyman goes to n equals 1. Balmer goes to n equals 2. I think bracket goes to n equals 3. Its passion is n equals 3. Thank you. Bracket goes to n equals 4 then. Is that right? Yeah. So this will then be 74. Okay. So there's quite a lot in this when you look at it. I'd have to say astronomers are incredibly good about getting information from these things. So they always amaze me how they manage to eke little bits of information around. They look at shifts, they look at the small lines, they look at the line shapes, etc. Sorry, I keep on forgetting to do this. So this is rather close at home. This is Uranus, ball of hydrogen. What do you notice immediately about these lines compared to the ones we were looking at before? The shape of them. So these are nice sticks. Yeah, exactly. Got someone waving his arms around correctly there. These are broad. These are broadened. And it's not just, I mean, it's not necessarily that high resolution. But you can see from the points on here that broadening is genuine. It's not just an artifact. Uranus, of course, is a cloud of hydrogen. It's quite high pressure. This almost certainly is pressure broadening, and we'll come on to that probably this afternoon. So this is, again, 1 to 0 S1, 1 to 0 S0, and the two Q branches. This is now in wavelength opposed to wave number, so it's flipped around with the Q branches on this side compared to the S0. And this is rather cold, so we don't see any of the vibrationally excited states we saw in the other. Uranus is, I think it's below 200 Kelvin. It's really pretty cold. In fact, the clue is written down the bottom there. It actually says they're pressure broadened. One more for you. This was a memorable one for me. So this is Jupiter. Very bad picture. I'm afraid this is taken from a very old overhead transparency. And a gentleman called Pierre Drossart, says Drossart et al. Up there, thought that he could observe the hydrogen spectrum in Jupiter. That predates actually that Uranus spectrum. So this is 1989. And he saw the S1 line of hydrogen here. He saw 28 other lines. He didn't have a clue what they were, and I don't expect you to have a clue what they are either. But it happened we were doing calculations on the H3 plus molecule, and those are our calculations. And actually, the fit is essentially perfect. It doesn't look quite perfect because these are two photographs on top of each other on our Xerox. And in those days, you had to do things on a Xerox. It was not quite linear. But essentially, we got perfect reproduction. That spectrum was not known in the laboratory. Well, let's rephrase this. That spectrum had been recorded at the National Research Council in Canada, but they didn't even know what molecule it was because they put hydrogen in a tube, in a plasma tube. They actually thought it was highly electron excited states of hydrogen, when it turned out to be H3 plus. And sorry, I thought there was another line on there. I think I'll come back to this on my talk on Friday. The interesting thing about this, but apart from being the first observation of H3 plus outside the laboratory, was that you got a temperature out of this. And our H3 plus is at about 1,000 Kelvin. And up until then, it was assumed the aurora of Jupiter. This isn't the aurora; it's the south pole of Jupiter, and it glows because it gets charged particles coming in down. Jupiter has a very large magnetic field; has charged particles coming down the magnetic field. It was assumed it was at about 500 Kelvin, and we told them it was double that temperature. So they had to completely change their models of what the Jupiter aurora looked like. Got 5 minutes, good, because I've just about got to the end, so that's perfect timing. So that's another hydrogen plus H3 plus. The H3 plus is just the standard, it's the bending mode actually. This was the overtone, this region, it's 2 quanta of H3 plus spectra, so it's a double jump. H3 plus is a funny molecule, the overtone happens to be as strong as the fundamental, but that's not usual. So just to summarize where we are on hydrogen, we haven't done the electronic spectra, that comes later. But you have the 21 centimeter line lying right out in the radio frequencies. You've got the rotational in the far infrared. You've got the vibration rotation in the mid to near infrared. And then we have electronic transitions, which are in the ultraviolet, which we'll talk about later. So that's just, and 21 centimeter, providing we don't all mess it up with our mobile phones, is in a nice clear region for observing. The other ones rather less so. So I think that's all I'll say this morning. Anyone got any questions before we have a lunch break? So that's a quick trot through vibrational spectra. I've got a little bit more of vibrational spectra, which is how we calculate them, but I'll do that this afternoon. Yeah. Sorry, intensity
variation.
Yeah.
Of the spectrum. The
Well,
reasons.
With
Vibration spectrum.
with vibrational modes or with
Vibration lines.
yeah. So in general, allowed stretching transitions are the strongest. So if you have an asymmetric stretch, for instance, or a molecule which has an inherent dipole that stretches, that tends to be strong lines. The bends tend to be weaker. That means that you tend to see overtones of the stretch, but not so much overtones of the bends, because they tend to be, by the time you get 2 or 3 or 4 quanta, they just tend to be too weak. So So when I talk about water being visible, being observable right the way through visible wavelengths, that's actually just the stretching limits of water.
The combination lines.
Yep.
So when basically it relaxes to two different vibrations.
So you're giving out quanta of two different vibrations in one motion. So that's not allowed in the harmonic rules, but it happens. And I'll talk. I think I'll start my talk about my work on Thursday, tomorrow, but Thursday, Friday, when I talk about the X1 project, you'll find these combination lines are really important in hot spectrum. There's not so much starting from the ground state.
So these are overlapped, or is it separate?
Sorry?
These lines are overlapped?
Yes,
they
they can be.
identify.
They can be. They can be. And what you'll find when you get hot is when you're a cold spectrum, you get the ammonia spectrum I already showed you, which has huge gaps where there's nothing. When you get hot, you fill in all the gaps. And I'll give you illustrations on that when I talk about what we're doing on exoplanets. Why it matters, if you model it wrong, you get completely the wrong answer. So hot spectra look very different from cold spectra. And we calculate them because some of them have billions, and I mean billions of lines. And I commented that there are simply not enough PhD students in the known universe to measure a billion lines for one molecule. So you have to get a calculator that's going to do it. Okay, any other questions before we wrap up? Yep.
Sir, the spectrum given us, you show.
Yeah.
Is it because only for pressure or
That's a good question. So the question I got was, if we go back to the spectrum of Uranus. Going the wrong way. There, you've got these line profiles. He said, is it Doppler broadening as well as pressure broadening? There is certainly a Doppler component. So Doppler is temperature dependent, and this is quite low temperature, so the Doppler effect will not be that big. This is, I think, substantially pressure broadening. But when you do it properly, and I'm going to go through line profiles at some point. I think I moved them from the end of the vibration rotations. No, maybe at the end. Maybe I'll do it this afternoon. I can't actually remember where I've got them in my talks. I moved them around. You'll see that you have to add the vibration, the Doppler and the pressure broadening together, and you get something called a Voigt profile, which unfortunately is not can't be sold analytically, so it all gets rather expensive. But there will be a Doppler component in there, but I think the major thing is pressure broadening. Though actually pressure broadening of hydrogen by hydrogen is very inefficient because hydrogen is very light. It's to do with molecules banging into each other. And because hydrogen is very light, you don't make much of a bang. If you have a heavy molecule or something with strong long-range forces like water with a dipole, you get a much stronger pressure broadening effect. But we'll talk about that later. You do see shifts. They're small, but you do see line shifts due to pressure broadening. I've got sucked into working on the theory of pressure broadening because it's important for exoplanets. I've not really worked on the theory of line shifts, but when I first started watching this, line shifts can go in both directions. And well, you've worked on some of this stuff. When I first worked on it, the theories would have a 50% chance of the pressure of the line shift going in the right direction. So it was not very good shape. I think it's a bit better now, but it's quite difficult to get it right. You don't most astronomical things you see are not hugely high pressure. I could ask you an unfair question, which is in what astronomical object do we see the highest pressure lines? You won't know the answer. You probably don't even know the objects. They're brown dwarfs. So brown dwarfs are failed stars. And it turns out, and this is slightly counterintuitive, that as a star gets more massive, the outer atmosphere gets more diffuse, so the pressure is lower. So the pressure on the surface of the sun is only about 10 to the minus 5 atmospheres, and basically you can forget pressure broadening, and it's all Doppler broadening. Go to even hotter stars, it gets less and less as the stars get cooler. So M dwarfs, which are 3,000 Kelvin stars, they're the most common in the galaxy. So the sun is hotter, as you probably know, it's more like 6,000 Kelvin. M dwarfs have appreciable pressure effects. Brown dwarfs are even cooler, and they're not massive enough that they never collapse enough to burn hydrogen. So they're sometimes called failed stars. And they get to, say, 10 atmospheres. And everything I say about pressure broadening later today, and this is something Bobby knows more about than I have because he spent a postdoc working on pressure broadening, and I've never seriously worked on it. Everything I say about pressure broadening later today probably doesn't work at 10 atmospheres, because everything we know about pressure broadening is based on binary collisions, saying while you do a transition, another molecule may come in. But obviously you get a big enough atmosphere, there's a chance of having two collisions at the same time. And I don't think there's a good theory for that. And I think probably for astronomical reasons there needs to be. And you get basically 10, I've already showed you the difference between CO2 in the gas phase and CO2 in the condensed, sorry, it was CO in the gas phase and CO in the condensed phase. Basically, you go towards, if you have a big enough pressure, you go towards a condensed stage type thing. You basically fill in all the gaps, you just get lumps. And you get a process called line mixing I'm not even going to talk about, but that gets very important at high temperatures, sorry, high pressures. You get all the lines mixed. So people still grapple a lot with this. I have to say it's a spectacularly unglamorous area of science to work on pressure broadening, but it is rather important because it really affects the way the spectra behave. And in particular, it affects the radiative transport because of this business of being saturated in the middle of the lines. Then all the pressure on the edge, the pressure effects on the edge tell you how much gets absorbed. And when I talk about exoplanet things, there are ways of taking exoplanet spectra where actually saturation effects are everything. So it becomes really important. So having given you a trailer for some of the stuff we'll do later on, I think we'll stop there and we reconvene at 2:30, is that right? Yep. So enjoy your lunch.